Hello, everyone. Welcome to my talk. So I'm Xuhua. I'm an associate professor in the School of Computing and Information Systems, SMU, here in Singapore, not the one in Texas. So it's my pleasure to come here and get this opportunity to share with you with our research work about a new dynamic software analysis framework. This is a framework that allows you to develop your program to dynamically analyze a kernel or even dynamically analyze a malware. So strictly speaking, this is not a new framework in the sense that we actually have published this paper in Auckland last year. But the reason we come to the Black Hat conference to share with you this work is mainly because we want to reach out to much broader audience. And we do have the belief that this framework called OASIS indeed can help many users in this community to address many dynamic analysis challenges. So later on, you can see what are the features our technique can bring to you. Okay, so here's my outline. I will first do a quick review of existing approaches for kernel analysis dynamically. And then I will introduce our work called OASIS, which is this called the Onsite Analysis Infrastructure. I will explain to you the analysis primitives provided by OASIS to developers. Here, developers are the ones that developing analysis tools. I will also show you two examples with some of the screen recording of our demo. Then in the end, I'll just wrap up with summary. So since we already published the paper elaborates a lot about the internal details of how OASIS works. So here in this talk, I will only focus on how a user uses OASIS. Of course, I will explain some high-level picture, the basic idea behind, but I'm not going to delve into a complex low-level issues of the internal working of OASIS. All right, so just a quick review. If you want to do kernel dynamic analysis, basically there are two approaches. The most common one is code instrumentation. You want to get some job done with your kernel, you add in your code to the kernel. And you may need to compile it if you do it statically. So there are two approaches for you to do instrumentation, static instrumentation or dynamic instrumentation. No matter what, in the end, what you get is the kernel whose code has been mixed with your analysis code. So your code and the kernel code will become one body, one binary. They will share the execution flow and share the address space. Then this is very wonderful because your code can easily get the job done. Your code will have this native access to the kernel objects, to the kernel memory. At the same time, because your code is in the same body with the kernel, then there are implications. One implication is this is intrusive. You have to modify the kernel, well, not to mention those hassles for the compilation. Modifying kernel sometimes doesn't work in scenarios such as you get a production kernel running in the virtual machine. Then you don't get the chance to do the pre-processing. Then from the security perspective, if you make this modification, then your kernel, your code can be compromised or detected or modified by the malware in the kernel. So suppose the kernel itself has been compromised, the adversary can easily modify your code and change your analysis outcome. So this is the bad. So that's why we get to the second approach, which is more from the academia. In the academia, when they look at this problem, they say, hey, let's don't do instrumentation. So let's use some hardware features to trap the kernel execution into a more privileged environment. That depending on the combination, let's say you can use virtualization, you can trap the kernel execution into the hypervisor. Or you may use the PMU to trap the kernel execution into the SNM. So the advantage here is, okay, you solve this transparency and security problem because your analyzer, your code stays outside of the kernel, is in a more privileged environment, so kernel cannot read or cannot tamper with your execution. Nonetheless, there are drawbacks. Since your analyzer is outside, then you lose this flexibility and a native access control to the kernel. There are several issues. One is when and where to trigger this event. This is entirely at the mercy of the hardware. You don't have the entire control. Secondly, when you do introspection, when you read the kernel memory, you are reading the kernel's physical memory. You're not reading the kernel's virtual memory. So this is something like you walk in the dark, in a dark room. You want to find out where is the door. So you have to fumble with your fingers to find out, instead of you can see it clearly. Lastly, programming in this special environment is tough. Let's say, imagine you need to write your analyzer in this SMM. It's a very difficult job. You don't have the library support, you don't have OS support. Everything you have is just a raw CPU. Okay, so we are asking this big question: can we combine these two approaches to get the best out of them? But we don't want their drawbacks. Meaning, we want to get the transparent and secure analysis. However, we want our analyzer, our tools, can have native access to the kernel, can do introspection, can do modification. Now, how can we do that? So we came up with the idea of, why not we interleave the target instruction stream with the analyzer's instruction scheme, but we don't mix code together. So imagine this: you have a CPU. This CPU will continuously fetch instructions, but sometimes it fetches the instructions from the kernel. Sometimes it fetches the instructions from the analyzer. So the analyzed code and the kernel code are physically separated, but the execution are kind of mingled together. So we call this execution flow instrumentation, EFI, to mimic the sense of code instrumentation. So we mix execution together, but we don't mix the code together. So, and we call such an analysis as on-site analysis. So the analyzer analyzes the target program, the target kernel, as if it were one part of it. The reason we name it after on-site analysis is because this is give you this intuition that it's not something like you are doing an on-site interview. So you go there, you go to this company's building, you meet their people there. Of course, you get the first-hand information about this company. Nonetheless, you remain as an outsider. So with on-site analysis, we're hoping that our analyzer can have this security, transparency, and native control. Then to do so, we need to satisfy a few requirements. Number one, we want this analyzer to dynamically choose the site of instruction flow interleaving. So we cannot leave this to hardware to decide. We need to have another analyzer to take the full control. So the analyzer can decide at any point of the program execution and the kernel execution, then you can do this interleaving of instructions. Secondly, we don't want the CPU mode or CPU privilege switch. If the target thread runs in the kernel in a ring 0, and our analyzer will also run in ring 0. If the target thread runs in ring 3, then our analyzer can also run ring 3. So the main reason behind this allows the analyzer to natively share the CPU context with the kernel, so they have the same computing environment. Lastly, this is the most important one. So we want to have this one-way address space isolation, meaning that the target address space can be accessed by the analyzer. So from the analyzer perspective, it can natively access the entire kernel space. However, not vice versa. The kernel cannot access the analyzer. So this is something like a one-way mirror in the police station's interrogation room. So the police officers can see everything inside the room, but the suspect cannot see things outside. Of course, the suspect can make a guess, but he or she doesn't see anything. So if we can solve these issues, then we get the secure and transparent analysis, and we can also have native access. The analyzer can read everything in the kernel's virtual memory, and we can allow the cross-space analysis, because this is the whole address space will be shared with the analyzer. Then how can we do that? So we design this infrastructure called OASIS. That stands for Onsite Analysis Infrastructure. So in this infrastructure, we consider the target is one thread, okay, not the program, one thread running in the guest VM. The analyzer is a normal application running on the host Linux. So this technically is is for Linux only, but the target can be any operating system, can be Windows. So when it runs, most of the OASIS job is done within the host kernel, and this OASIS will create the on-site environment, as I show here. In this on-site environment, this on-site environment has a dedicated CPU core. So this environment doesn't have operating system, and only two threads running on the CPU. One is analyzer, the other is target. So their instructions will be interleaved together. And this on-site environment also has a special paging hierarchy. We will give a special PML4 page for the MMU to do translation, but the on-site environment does not have any dedicated memory pages. All the data, all the code of the analyzer is managed by the host OS. The target runs in the guest VM. So in this on-site environment, we're going to run on-site analysis. So let's see a high-level picture of this workflow of on-site analysis. So you get two environments. One is the on-site environment. You get a dedicated on-site core, and we also grab one core from the guest VM. So we export the target thread to the on-site environment. There we conduct this on-site analysis within this on-site environment. Once the job is done, then the analyzer can release the target. The target can continue to execute in the guest VM. Then you can repeat this cycle. You can periodically or randomly pick one thread to analysis. After a while, you can release it later on in the guest VM. If needed, you can catch it again or catch another thread to do analysis. Then within this on-site analysis, it's basically is composed of this cycle of execution between analyzer to the target. So we use term exit and entry. Exit refers to the control flow will pass from the target to the analyzer. The entry means from the analyzer to the target. So this is how if you run your analyzer on top of OASIS, this is the flow. So let me explain to you what are the primitives that allow you to develop your program, your analyzer. So the number one primitive is actually doesn't require special APIs from OASIS. OASIS allow you to natively access kernel memory, meaning given any kernel address, kernel's current virtual address, you can easily use it as if it is in your code, it is in your program. Then you can, let's say you can visit a kernel here, then you can do direct memory copy. All the standard libc libraries can be used without additional treatment, because this is part of the analyzer. You can do memory copy, you can read the memory, you can copy the memory. And you can also do printf. You can also use networks. You can also use file, because the analyzer is a normal user space application running in the host. So let's see one demo here. This is the video recording. So we have the analyzer on the left side of the screen. There are two windows. The one belongs to the guest VM. The top one is the guest VM's kernel output. The one at the bottom is the target. Okay, so let's play it. Let me play it. Okay. Yeah. So here, in order for the purpose of demo, then we made some changes on the guest kernel in order to print out something. So here, the kernels, our kernel module will print out some of the key ring and content binaries. Then we run the target, and we export the target thread to the analyzer. Then the analyzer will print out the kernel memory easily. Here the analyzer is given a global variable of the kernel address. Then just do the dereference, find out the virtual address of this key ring. Then just print out the binaries. Then in this object, there's one pointer pointing to another object called a key user. Then this analyzer will just print out this key user object. So these two binaries are identical. So the good thing here is you can easily use any standard libraries to process the kernel memory. And OASIS guarantees that whatever you see from the kernel virtual machine, from the kernel's virtual memory, is exactly the same from the kernel currently runs. So there's a consistent memory view. Okay, then with this one, you can with this one you can write your analyzer to process whatever analysis task you want, but it doesn't provide you the control. Then how can your analyzer control the target operation? Well, we introduced three mechanisms for you to control the target thread. One is the traditional inter-3 probe. So we place this 1 byte in the kernel's code anywhere you want. Then once it is triggered, then this interrupt handler will transfer the control to the OASIS exit gate. So this exit gate is basically a couple of instructions. I won't go to the details here. Basically, this will make a paging hierarchy switch so that the instruction runs afterwards will be from the analyzer's address space, not the kernel's address space. That's why we call it exit gate, meaning the control, the execution flow will switch from the target kernel to the analyzer. We also have this JMP probe mainly for control flow and tracing. That can replace certain bytes that allow you to jump this exit gate. We can also allow you to do this event interception, so you can catch kernel page fault, interrupt handler to do the analysis. So one caveat here is these changes are only effective for the target thread running in the on-site core. The entire guest VM is not affected. Secondly, although we make changes on this on the code by adding probes, we may also provide a handler, but all these changes remain transparent to the kernel, to a target. The target doesn't see these artifacts. This is by using virtualization techniques. Again, the details are in our paper, but of course I will be happy to explain later on. Then how do we resume the target? Once you've done your job, how do we put it back? Well, you can just jump in, allow your code to jump to the entry gate, so the control will be passed back to the target. At this moment, then you can choose where to resume. You can choose the RIP for the target kernel to resume. So let's look at these some examples. The first one is to use the inter-3 probe to add the breakpoint in the Kmalloc function entry. So what your analyzer will only be composed of two functions. One is the main. So in the main function, you set this probe in the location of this Kmalloc address. Then you just resume the program. Resume the kernel. Then so when the kernel runs, it encounters this Kmalloc. Then this int3 will hijack the flow and pass it to this int3 handler. So your handler will run, you do some analysis work, then you can decide, should I remove it or should I keep the kernel run? Okay. Then if you use this control flow tracing, then it's a little bit more complicated because you have to calculate where to put the probe. So initially you put this the probe in the basic block exit, then resume target. So target will run, go to the handler, this jump handler, the handler will just remove the previous one, then set a new probe to the next block based on your calculation. Then you resume the target will continue to run. Okay. So this jump probe is mainly for control flow tracing. This int3 mainly for the code breakpoint. All right. Again, we have a short demo here. So again, we run this. There are three windows. The analyzer on the left side. There are two windows about the target on the right side. So one is from the guest VM output. The second, the one in the bottom is the information about the target thread. So in the target here, the target thread will issue two syscalls. First are get priority with different arguments. Then we export the thread to the analyzer. So the analyzer will do two things. One is to install int3 probe at the entry of this get priority. So you can see this get priorities handler. Sorry, this get priority handler is triggered twice. Then in the second triggering of this handler, then we can do basic block tracing. Here we only trace 5 blocks. Of course, you can trace it to the end. Okay. So to wrap up, OASIS give you this some of the new features for kernel analysis. It is thread-centric. It allows you to make a surgical analysis. It's not good for large-scale code-centric analysis, such as profiling. You want to observe the kernels as one whole piece of work. If you want to observe some global effects, sorry, this OASIS may not help you. But if you want to make say debugging, then that is a very good application. The second feature is it allows you to make a native access to the kernel memory and to the CPU context. It has a strong security and transparency. Your analyzer is immune from attacks from the guest kernel because they are separated physically. It's protected by the underlying paging hierarchy. And your program, I think this is the most attractive one. Your program remains at the user space application. You are free to use libraries, make syscalls to build your analyzer. And you don't need to worry about, okay, I'm programming the kernel, then what kind of service I can use. You can do it as like a normal application. There are a few potential applications. You can do VMI, you can do the kernel debugging, you can do cross-space malware analysis. You can also do the attack forensics and to respond to the attack. Okay, so,
5 minutes, Professor.
Work.
5 minutes.
Yeah, thank you. I want to leave some time for Q&A session. So to wrap up, this is the Black Hat soundbites, basically the main takeaways. So main takeaway here is with OASIS, what you can do is you can easily develop and run a user space application. This application allows you to dynamically and natively read and write control the target thread in the guest VM. So regardless the threat is in the user mode or in the kernel mode, you can also do the analysis. And you do not need to pre-process in the kernel. There's no modification of the kernel is required. There's no, we don't need the source code. We can apply this on Windows. It has strong security and transparency. There are a bunch of suitable applications from our understanding, such as VMI, such as kernel debugging or the malware analysis.